In the chapter you read yesterday, you covered a lot of concepts that I don't need to walk through with you because I already demonstrated them in a previous video. Things like the mean, median, mode, range, standard deviation, and even how to split these pieces of output by different grouping variables. However, I am going to show you some other concepts that the chapter kind of walked through that we haven't been exposed to yet, like the frequency table, the interquartile range, skewness, and kurtosis, and z-scores. And where I'm going to start is by showing the difference between different kinds of means that you can compute in Jamovi. So, in order to demonstrate this, I want you to go first to your menu and open a data file that is included in your data library for this textbook. If you scroll all the way to the bottom, the last one is called Personality Questionnaire. I want you to click on that and go ahead and open that data file. I'm going to walk you through a little bit of what this data file is when it opens up. You'll see that there's 5 different lettered variables. If I expand this over and reduce the size of our output window, you can see more of your data. So you've got first an ID, which is the participant numbers for each of those rows. So you've got person 1 has this ID, person 2 has this ID, etc. And each of these people has filled out a questionnaire that has a lot of items. All these variables are items in a questionnaire. And they start with things like A, and then C, 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 C. And if we scroll over, you'll see that it starts with 5 of these start with E, 5 of them start with N, 5 of them start with O. And if you've been a psychology major for any length of time, you probably recognize this as the Ocean Personality Big 5. So those stand for openness, conscientiousness, extroversion, agreeableness, and neuroticism. So we have 5 items that people answered for each of those sub-constructs in the personality inventory. So this A stands for agreeableness, and if you kind of look at these for a minute, you'll realize that A1 is an item, a survey question about agreeableness, and A2 is a survey item about agreeableness, but a different one. And agreeableness, of course, is like how kindly and empathetic and just overall agreeable or amiable you are in life. So this first item might say something like, I tend to trust people and give them the benefit of the doubt. And the second one might say something like, I am extremely empathetic. And the third one might say something like, I like to make other people feel at ease. And it would go on with a couple more. These conscientiousness scales would say different things about how conscientious or self-aware or self-controlled you are. If I double-click on this to bring up the source information, this metadata about the variable, you can see that there are 6 levels. 1, 2, 3, 4, 5, 6 levels, which means that these people filled out a survey where those were the 6 possible values they could have responded with. Each of these was probably anchored with a word, and they probably ranged from something like strongly disagree, and then they might have said like moderately disagree, and then slightly disagree. And because this is a scale with an even number of items, there's just 6 rather than an odd number like 7, there can't be a middle point. There's no neutral. There's nothing that says like neither agree nor disagree. So we have to just skip after we see slightly disagree. That means that it was probably something like slightly agree, and then moderately agree, and then finally strongly agree. Now, I don't know if those are the exact words that were used, but I surmise that they were because that's very common to use on a Likert type analysis. If I push enter here, then of course it will fill in for me the names of those things in A1. And I could go ahead and fill that in for each of the items in the whole scale, but there are 25 items, and there's not, as far as I can tell, any easy way of copying these levels into additional variables. Like if I came over here to A2, I couldn't just autofill those same 6 values here and do that same thing for each of the variables. It's my understanding that because Jamovi is a free open source piece of software. The people developing it are doing this for free. They're not getting paid for it. They're not getting paid for licenses of it, and therefore they're just doing this as they can in their spare time. What that means for us is that the functionality is sometimes limited, and in future editions, these people are planning to develop additional features that will allow you to quickly and easily copy and paste things like this. But right now, it doesn't yet exist, and so we just have to be patient with difficulties like that. It's just instead of paying a financial cost, you pay just like a time and effort or a cost of ease to yourself for using a software like this. Now that we've kind of talked about the structure of this data set and what it entails, I want to take a minute and talk to you about what we might do with these data as far as the mean is concerned. So you remember that if we wanted to just compute the mean of, let me get rid of this. If you want to compute the mean of an individual variable like A1, then we would just bring it over here, and it would automatically spit out in the output the mean is 2.37. And if you remember the scale, that was something like moderately disagree. That's the average of how much people agree with whatever statement this was. However, if you are computing the average of just one item, or even if you wanted to compute the averages of all of these agreeableness items, you would be somewhat limited in what you could do with that information. In reality, in scientific research, you probably would want to aggregate all of these agreeableness items into a single scale. So you'd want to take the average of everything they're saying about their agreeableness levels and kind of put them all into one average scale. And so the way you would do that is computing a mean within the data instead of here within the output. So I'm going to get rid of the descriptives analysis option and go back to your data. And here I'm going to want to add in a computed variable, but in order for it to make sense where it's located in the data set, I want it to be after all 5 of these A or agreeable variables. So I'm going to put my cursor here after A5 and then click compute, and it will insert a new variable right next to A5, and I'm going to call this variable, it defaults to G, but I don't want to call it that. I'm going to call it agreeableness. And in order to compute agreeableness, I'm going to just type in here the mean of, and then open parentheses, A1, comma, A2, comma, A3, comma, A4, comma, A5, and then go ahead and push enter, and that will give me an agreeableness scale. I can then take this and go back to my analysis and figure out what is the average agreeableness. So I can take this agreeableness scale, put it over in my variables, and it will tell me the average agreeableness is 4.2. That's much more useful than having 5 individual agreeableness values of averages for separate questions. Now that's a useful thing, but at this point you might be wondering, or just a minute ago you might have been wondering, well, how did you know to type in capital MEAN and then open parentheses and separate all those things by commas? Well, let me just walk back here for a second to the data, and I'm going to show you a different way you can do that. Because I'm familiar with the syntax that's being used here, and because it's pretty standard across different statistical packages, and it's the same one used in SPSS and the same one used in R, I already knew that the structure would be mean, open paren, and then a list of variables. But if you weren't familiar with that, you could say we want to compute an average for the conscientiousness variables here, C1 through C5. I'll put my cursor here, insert another computed variable. It will insert right next to C5, so I can call this conscientiousness. Conscientiousness. I think I'm spelling this wrong. Conscientiousness. This conscientiousness variable is going to be, again, the average of C1 through C5, but if I don't know the syntax for how to compute a variable, they have pre-programmed functions in here. So if I click on this, it will show me the formula editor, kind of like a wizard for how to structure my formulas. If I click that drop-down arrow, I can see that different functions are organized by math things, statistical things, and there are more categories. But here I see the mean, and that's what I'm looking for. If I click on mean once, it tells me the syntax, how to organize this. It says you type in capital M, capital E, capital A, capital N, open parentheses, and then you list your variables separated by commas, just like I did before. It says ... for indicating, like, continue to list whatever variables you want, and then if you also want to add in whether to ignore missing values within your data set, then you can tell it yes or no based on 0 or 1. And then finally it tells you what this is going to do. It returns the mean of a set of numbers, and that's indeed what we want. We want this set of numbers for a participant here, 1 through 5, to be averaged together. And so I'm going to come back here and I'm going to say I want to double click mean. That will bring up the basic structure of the function. It will leave my cursor in between those parentheses, and now I can come over to what variables I want to include, and I double click C1, and then I insert a comma just like it told me to. Double click C2, comma C3, comma C4, comma C5. And when I finish, then I push enter, and it will compute again the mean for me of C1 through 5 for each of the people. So the average of person 1's 5 conscientiousness variables is 4.2, and that makes sense since they had 5, 5, 5, 1, and 5. So this 1 kind of brought it down from being an average of 5 down to a 4.2. This person had 5, 6, 6, 2, 6, and their average is therefore 5. So this is giving me an average for each person across those 5 variables. Now the reason I'm telling you that is because in a minute we're going to compute a different kind of mean, and I want you to remember right now that this is computing by rows, individual people's averages across variables. Once we, like I said before, once we do that, we can do some additional interesting things in our analysis tab, and that's the reason why I've showed you that. Another thing the chapter talked about in our reading, I'm going to open up the reading for a second, is standardized scores, or z-scores. And remember, z-scores are equal to the raw score, whatever that person's score is, minus the mean of all the people who got that value, divided by the standard deviation. And in statistical notation, of course, that's the z-score for any individual person, that's represented by I. Z-score for an individual person is equal to the score that that person got on that variable, that individual, individual got that score, minus the mean of all of the scores in that variable. Okay, so it's finding the distance between how far is this person's score away from the mean of the whole distribution, and then dividing it by the standard deviation of this variable, so that we know how far away it is in standard deviation units. By computing this, we can understand relationally how each person's score falls within the set of all the possible values that people might have got on that variable. So I'm going to show you how to compute this in Jamovi. Now, z-scores are not something that's computed in the analysis tab, because the analysis tab is going to show you aggregated things across people. Like, it's going to take everything for a variable and give you like the average of all the people in a variable. But a z-score isn't like that. A z-score is an individual thing. Each person will have a z-score. So like if I wanted to convert this whole conscientiousness scale into z-scores, then I would have to take the first person's score and find out how far away it is from the mean of this entire set of scores, and then divide by the standard deviation of this entire set of scores. So I'll show you first conceptually how you might do this. This is not the actual way that I want you to compute it in real life. I'll show you that in a second, but just so that we understand conceptually, I'm going to go ahead and run an analysis here on conscientiousness. So I'm going to go to Descriptives, and I'm going to say, I'm going to take this conscientiousness score, plot it over here, and I'm going to say, I want the statistics of the mean, not the median, and the standard deviation, because that's what I need to compute a z-score. So what I need to do is for each person in this data set, coming over here to conscientiousness, I need to take each person's conscientiousness score, subtract from it the mean of that set of scores, 3.82, and then divide it by the standard deviation, 0.574. So I'm going to hide this descriptives box for a second, this analysis box, and I'm going to go back over insert a computed variable next to conscientiousness, and I'm going to call this z underscore conscientiousness. Okay. So this right here is going to be a z-transformed conscientiousness variable. And what I want to do is for each person, I want to insert their conscientiousness variable. I'm going to, again, drop down my functions, insert the conscientiousness variable, and I'm going to subtract from it the mean, which was, as we just computed, down here 3.82, and I'm going to put that in parentheses so that we can divide the whole thing by the standard deviation, 0.574. Alright, remember, I'm just going to show you once more, that's the z formula. The score minus the mean of that set of scores divided by the standard deviation. So the score, conscientiousness, whatever that person got on that variable, minus the mean of conscientiousness, which we just computed here, divided by the standard deviation of consciousness, which we computed there. If I push enter here, that will give me this new variable of conscientiousness z-transformed. So if you take a look here for a second, you'll see that this person is 2/3 of a standard deviation above the mean. So the mean of conscientiousness is 3.82. This person got 4.2, and that is, if the standard deviation is 0.574, they are about 2/3 of a standard deviation above that value right there, 3.82. So 2/3 of 0.574 is that, since that's the standard deviation, 2/3 of that is how far above 4.2 is from 3.8. Hopefully that makes sense. That is not how I actually think we should compute this, because there are specific formulas that will allow us to not have to do this kind of analysis here first. Instead of putting in 3.82 and 0.574, I can use a different, I'm just going to put in a placeholder here, star, and I'm going to put in a placeholder here, star, and I'm going to replace those values with formulas instead, so that whatever happens in the future, I can just, it can just automatically update, and I don't have to go and compute this first and hard code these values in. So I'm going to drop down my formula box here, and I'm going to say, actually what we want is the mean of all the conscientiousness variables here. But if I use this function, mean, remember that gives me variables summarized, the average of variables summarized in rows for each person. And I don't want that. I want the average of conscientiousness as a variable computed vertically rather than horizontally. And so in order to get that, I have to find another kind of mean that is labeled v-mean, v for variable mean. So this right here will be, or vertical mean. This vertical or variable mean will give me a different value. It will compute for conscientiousness as a variable instead of each row individually. So I can plot this in here. I'm going to get rid of these stars now. I plot in v-mean, and then I insert in there what variable I want it to compute the mean of, and that's conscientiousness. And then I want it to divide by the standard deviation of consciousness. And the standard deviation is typically the function stdev for standard deviation. But again, that will give me for rows, individual people across multiple variables. And that's not what I want. What I actually want is vertically or variable standard deviation. So I use this v_stdev. And so if I double click that, and in the parentheses I put conscientiousness again, what I'm doing here is I'm saying, I want you to compute for me conscientiousness, the individual value that somebody got on conscientiousness, minus the mean of the conscientiousness divided by the standard deviation of conscientiousness. And that should give me about the same values that I got before. It might be a little bit different because this, of course, right here was rounded. This mean and standard deviation were rounded to just a few decimal points. When I have it computed here, it doesn't have to round at all. It can carry this out to 10 or 20 decimal places, and so these will be slightly different than before. Like this first one was 0.662, now it's 0.666, and the reason for that, again, is a difference of rounding. So that's what you can do with like that's how you compute a z-score. But then if you want to come over to your analysis tab, you can look at the distribution of z-scores now. So if I take this conscientiousness and I plug it over here, then I can see that remember the z of z, if somebody has a z of 0, that means they got exactly the same as the mean, and the mean z-score in a distribution is always going to be 0. Well, what you see right here is not actually 0. What is this weird number right here? This is in scientific notation. It's actually saying 1.77, negative 1.77, times 10 to the negative 16th. So that means there's 16 zeros before this negative 1.77. So it's like actually negative 0.000000000000001.177, and that is pretty much 0. The reason it's not exactly 0 is because of some rounding difference somewhere, and it carried it out too far, and got a slight, like just a tiny bit off from 0. But theoretically, and if we didn't round at all, if we carried it out an infinite number of decimal places, we would always find that the mean of a set of values once transformed into z-scores would always be 0. In this case, it's virtually 0. It's not exactly 0, but it might as well be. And then, of course, we've got the lowest z-score in this data set is negative 3.86, and the highest is 3.45. That means this is nearly 4 standard deviations below the mean, and this highest score is a little over 3 standard deviations above the mean. You can also ask for a plot here. If you ask for a histogram, you can see that these should center around 0. Right there is 0. You've got z-scores that center around 0. You've got some that are above 0, some that are below 0, but most of the z-scores will fall around 0. And usually 95% of z-scores will fall between negative 2 and positive 2 standard deviations from the mean. Alright, so that's a little bit about z-scores. Another thing that I want to tell you about is frequency distribution tables. So I'm going to go ahead and take out our z-conscientiousness variable here, and I'm going to start with something different. Let's say that we wanted to figure out what is the percentage of people who agreed or disagreed with different values of this first item in the agreeableness scale. So if I plug this over here into my variable list and I click this box that says frequency tables, this will give me a frequency distribution table of how many people strongly disagreed, moderately disagreed, slightly agreed, moderately agreed, and strongly agreed. This is the number of people, that's the count, how many people in the data set endorsed those statements. And this is the percentage of people that endorsed those statements. So 34% strongly disagreed, 28% moderately disagreed, 15% slightly disagreed, etc. This cumulative percentage is adding up these as it goes. So the utility of this is, say we wanted to know how many people disagreed with this statement. We could say 34% strongly disagreed, but we wanted to add to that how many people moderately disagreed, 28%, and that would come to 62. And we'd also want to add to that how many people slightly disagreed, and that'd be another 15 for 78 or so. So 78% of people disagreed with this statement in some degree, strongly, moderately, or slightly. They disagreed in some degree. And then, of course, the inverse of that is all the rest. So another 22% or so agreed with the statement here as the rest. So that's the utility of the cumulative percentage total. You can see how many people said, as we go and add them up. This frequency distribution table can be computed for only these two types of variables, nominal variables and ordinal variables. In other words, for categorical kinds of things. Remember that each person who filled out this survey could only say one of these 6 things. There was no option to say something between strongly disagree and moderately disagree. They just had to pick one. And so when they picked one, that meant that this scale of measurement was an ordinal scale of measurement. Well, in the data set, it's labeled as nominal. Obviously, that's not correct because these are ordered, right? And one could even go back and change them into a continuous variable represented by this ruler. if they theoretically wanted to do some different kinds of statistics using that idea that the distance between this one and this one is the same as the distance between this one and this one is the same as the distance between this one and this one, then you could call it like continuous, even though like theoretically we can't guarantee that the distance between each of these levels of agreement are actually the same. But for now, I just want to make the point that here this will allow us to compute nominal or ordinal, but if I have a continuous variable and I put that over here in the variable list that I want it to compute for me, it will not give me another frequency distribution table. It will give me a plot because I've asked for that already. In fact, I can unrequest that and it will get rid of it. But it did not give me a new frequency distribution table for this second variable here. And if I take out this variable that it did give me a table for, then the table will disappear entirely. Even though I've technically asked for it, it's saying I can't give you a frequency table for a continuous variable like this that's represented by a ruler. That icon doesn't appear in this list. And the reason it can't give that to me is because there's too many different values that people could have got. If you look at all the things that people could have said on this agreeableness aggregated scale, one person might have said 4.8, one person said 5.4, 4.2, one person got 3.6, 4.6, 2.44. There are too many different things. A frequency distribution table would be too long and too laborious, and it wouldn't even make that much sense to kind of group things together by how many people said each exact decimal point. So it won't give me the table for that. The next thing I want to talk about is a concept of the interquartile range. Remember, you read about this in your in the textbook, and the way you get this is by checking this quartiles. It will update our table here to tell us not only the minimum and maximum, but the 25th percentile, the 50th percentile, and the 75th percentile. And hopefully this made sense to you when you read in the text, but I'm just going to explain really quick what these represent. The minimum is the lowest score somebody got on this agreeableness scale. The lowest person scored 1.2. The highest person, the maximum, scored 5.8. Right in the middle, in 50%, half of people scored lower than 4.4 and half of people scored higher than that. That's the 50th percentile. That's the same as the median. The median conceptually is where is the midpoint, half below, half above. And that's the same as the 50th percentile. Well, we can say the same thing about a 25th percentile and the 75th percentile. So what this represents is the 25th percentile is saying where is the cutoff that 25% of people got lower than this value. So the lowest value is 1.2, the 25th percentile is 3.8. That means 25% of people got between those two scores. 25% got above 1.2 and below 3.8. The 50th percentile is 4.4, which means 50% of people got between 1.2 and 4.4. And the 75th percentile is 4.8, which means 75% of people got between 1.2 and 4.8. Now, the last 25% of people got between this value and the maximum, 5.8. So that final 25% is between this demarcation and the max. This might make better sense if we use a visualization called a box plot that you're going to read about in the next chapter that you cover, but I'm just going to kind of superficially start talking about it here. So I'm going to request a box plot for these values, and the box plot represents the same thing as the quartiles. So you'll see that in this box plot right here, the 50th percentile is the median is marked right here in the dark line in the center of this box. That corresponds with 4.4 on this graph and 4.4 up here in your table at the 50th percentile. You've also got a 25th percentile right here that's marked at 3.8. If you look at the scale, 3.8, it also says 3.8 up here. And the 75th percentile is the top of this box. It's labeled as 4.8 on this graph and 4.8 in the table. Now, the highest and lowest values are also shown in this box plot. The highest is 5.8. That's represented right here at the top of this line. That's 5.8. And the lowest value is 1.2. That's represented down here by this dot. Now, that might be a little confusing. You would expect that this line should go all the way down. But statisticians, in order to kind of demark the middle of the bulk of the distribution have indicated that it would make better sense to kind of define what the end of the line should be. And on the top side, the end of the line is in fact the maximum score. It's 5.8. But on the low end, in this particular distribution, they've decided to demark this as the lowest point that's 1.5 interquartile ranges below the median. Now that's really confusing and difficult to understand. But this right here, this middle 50%, this blue box, represents an interquartile range. That's the middle 50%. If we take 1.5 of those, so if we kind of go, if you look at how halfway across that box would be right where my cursor is going across right now. If we went that far above the box and we kind of demarked a box that went halfway above and halfway below, then you could kind of imagine a box that's like 50% bigger than this one that we've already drawn. Okay? If we took that box and we moved it down so that the top of that imaginary box we just drew is at the median, and then the rest of it comes down here, the bottom of that box would be where this line is. And then everything that's lower than that, or if we moved it up, everything that's higher than that would be called an outlier, and we represent those by dots instead of just drawing the line forever. That, again, seems pretty absurd and kind of arbitrary, but that's just convention. We've just decided to call anything beyond 1.5 interquartile ranges an outlier. And so these 3 points right here are considered to be outliers. This bottom one, 1.2, is the lowest value in the data set. You can see that's represented there on the y-axis by 1.2 and in the table as 1.2. You can see that these two outliers are not listed in the table up above. This is like maybe 1.9 and this is like 2.1 or 2.2, and they're not listed in the table anywhere because they're outliers that aren't represented by the minimum, maximum, 25th percentile, 50th, or 75th percentile. They're not any of those things. They're just other outliers. And this right here, this value at the bottom of the line, is also not represented in the table anywhere because that isn't one of the percentiles and it's not the minimum and maximum. It's just an arbitrary designation that's 1.5 interquartile ranges below the median. So again, these aren't represented, but the lowest and the highest are represented here as minimum and maximum, and the 75th, 50th, and 25th percentiles are represented in the table right there. Now, if we wanted to get more precise than just these 4 little cut points, so that we, or I guess it's 4 equal groups, it's 3 cut points, but it's 4 equal size groups, then we could remove this quartiles here, and we could say we actually want cut points for 10 groups instead of 4. Or whatever size you want. You can, but 10 makes sense to me. So I'm going to put 10 and then enter, and this will divide it into the 10th percentile, 20th percentile, 30th percentile, 40th percentile, 50, 60, and so on. Each of those values is indicated, is telling you like what percentile, what percent of people are lower than that score. So if you took this agreeableness scale and you got like 4.7, then you'd have to say, okay, I fall somewhere between the 70th and 80th percentile. That's where my score falls. So I'm in maybe like, I'm guessing here, maybe like the 75th percentile or something like that. Okay? You might want to know the exact percentile. Like when you get your SAT scores back, you might say, oh wow, I'm in the 87th percentile, or I'm in the 42nd percentile, and that tells you how many people got lower than you. In order to get that, you'd have to come down here and put 100 in the box. But if I do this in Jamovi, it doesn't like to do this. So if I push enter here, it will give me an error, and it will say the value for this must be between 2 and 10. That's all it will give me. And right now it's 100, and it doesn't like that. So it's not going to give me something as precise as I want. Therefore, I'm just going to come back here and put in 10 and let it compute just, 10 boxes for me. I might even just take that away. Because the next thing that I want to talk about is computing skew and kurtosis. So as you read in your text, actually, I'll go back to your text for a second, and I'll just come up here to the section on skew and kurtosis because these visual images are going to help us a bit. As you learned in your introductory statistics class, a negatively skewed distribution has most of the scores on the positive side and outliers on the negative side. These outliers are pulling the mean towards this direction. These are the outliers. They're skewing the distribution. Therefore, the tail tells. That's a phrase that you might have heard. The tail tells, and that's how you know whether to call this a negative distribution, a negative skew, or, like you see here, a positive skew. If the outliers are in the tail on the positive side, then you say it's a positive skew. Having no skew means that it's equally balanced and it looks like a normal curve. Now the other principle here is the principle of kurtosis, which you learned as well, but probably didn't talk about very much in your introductory psychology class, or your introductory statistics class. If you look at this overlaid normal curve, that normal curve represents like what a normal distribution should look like, what the bar should look like if it were actually normally shaped. Now, sometimes you may have seen normal curves that looked a little flatter and some that looked a little taller, like this, like these kind of pointy one. That can happen because you can rescale the y-axis and kind of make a normal curve look flatter. The problem is, no matter how you rescale this particular normal curve on the y-axis, it will never match the look of this platykurtic distribution right here that's too flat. And so that suggests that the bars underlying this distribution have too, it's too flat, too fat of tails, too low a peak in the middle. And a platykurtic distribution, no matter how you rescale the normal curve that's overlaid over the top of it, it will never match. A leptokurtic distribution, as you read in the text, is kind of too pointy. You can remember these two terms, platykurtic and leptokurtic, because plat sounds like flat, so platykurtic is kind of like flatokurtic. It's too flat, not pointy enough. Leptokurtic is kind of like it's leaping up in the air. It's jumping up too high, so it's leaping, leptokurtic. And that will help you, anyway, that will help you remember like which is which. The values for interpreting both skewness and kurtosis are if it's fine if the values fall between -1 and +1. If it gets beyond that, then it becomes problematic. It means it's too far skewed, or it's too platykurtic or too leptokurtic. Now, I always seem to forget that, and so I just sometimes when I need to know what's going on, I just come and I Google and I say, how to interpret skew and kurtosis, and I'm just going to click on this first one, and you can just easily see that a common general guideline for skewness is that if the number is greater than +1 or lower than -1, this is an indication of a substantially skewed distribution. For kurtosis, the general guideline is that if the number is greater than +1, the distribution is too peaked, and if a kurtosis is less than -1, it indicates the distribution is too flat. So that, if you forget how to interpret, you can just Google it, and that will tell you a generic interpretation. If we come back to our data set now, we can ask for skewness and kurtosis values, and it updates our table here to tell us the skewness is -0.94 and the kurtosis is 1.24. -0.94 is pretty darn close to -1. Now, it's not technically over that threshold, so we might choose to ignore the problem if we are statisticians. But because it's so close, if you really want to trust your statistics, if you really want to be assiduous about this, then you might choose to deal with the skewness using strategies we'll talk about later. The kurtosis does violate the assumption because it's above +1, and so that means this is has too high of kurtosis. Now the way we know that, I'm going to get rid of this box plot and ask for a histogram. The way we know that that's what's going on is we can visualize this, and you can see that indeed there are a bunch of outliers here on the left side. That's the reason why it has a negative skew, because there's actually outliers on the negative side. And you can see that this bar here, for instance, is leaping up too far, which gives it this problem with kurtosis. So this is leptokurtic distribution. And you can see that again, it's the positive value 1. If it was too flat, then it would be negative something, right? So if you have skewness and kurtosis values, you can interpret those, and you can choose based on what you're finding whether you're going to deal with the problem or not. Another way you can tell if it's sufficiently problematic and you need to deal with it is this Shapiro-Wilk test. It's categorized as a normality test, and if you check on that, it will give you a value here, Shapiro-Wilk p-value. And the p-value, as you remember, is usually a demarcation of 0.05. In this case, it's asking, is this distribution normal? And if you have a value that's less than 0.05, then we would say that's not normal, it's problematic. And because this one is less than 0.001, we would say, oh wow, this is definitely not normal. And so we might have to choose to deal with it, again, using strategies that we'll talk about in future chapters. But right now, suffice it to say that we've measured our skewness, we've measured our kurtosis, and we've measured our normality, and we find that this is not a normally distributed, this is not a normally shaped distribution. That's all I wanted to show you tonight in this homework, or in preparation for your homework today. So if you have any questions, please let me know, but otherwise, good luck.